Hey, seventh grade. I am gone today, so this is what we are covering. We're talking today about evidence for evolution and what is the evidence and how do we support the theory of evolution. So, um, let's start by putting our learning target in our notebook. You guys can see that we're going to put our learning target on page 163. The target today says, I can describe the supporting evidence of evolution. Okay, so your note sheet today that the sub should have handed out to you will have 6 different sections. Each section represents one of the supporting pieces of evidence for evolution. Your note sheet should look like this. You'll see you have fossils, homologous structures, vestigial organs, comparative embryology, DNA sequencing, and artificial selection. When I tell you to, you will write your notes in these spots here. Okay, so make sure that when I stop you that you write them in the appropriate spot. Okay, so here we go. The first piece of evidence is fossils. This is the easiest one to think about, ones that we've seen since we were kids. We have bones that we find in the ground, and they look similar to the bones that we have today. So, the definition that we're going to write down says, we can see animals and plants are similar to the fossil remains of past organisms. So as organisms evolve, right, their bones are going to change a little bit, but there's still a lot of similarities. And here's an example. You can see here the whale. We know the whale, its common ancestor, used to walk on land. And here's some of those bone structures. Now, some of the bone structures that we look to see for are the pelvis and the hind limb. You can see here and here. Also, if you look at the snout, you can see how the nostril, a long time ago, 47 million years ago, it was more towards the front of the nose, kind of like a horse. And then it started to move upwards a little bit until now it's up at the top of their head, the blowhole that we know of today. So fossils are the first piece of evidence. So let's write in our notes now. Second piece of evidence is homologous structures. That's how you pronounce this word, homologous. So a homologous structure, basically, what we can use here is that many of the same skeletal elements make up the forelimbs of humans, cats, whales, bats, and all other mammals. What that means is that if you look at the arms of all these animals, they all look similar. So here's the picture that I have for you. So here's a human arm, cat, whale, and bat. So the things we're going to write down today are this. Homologous structures are similar structures, but they have different functions, and that is evidence of common ancestry. So if you look at the human arm, you have some color-coded bones. This is the forearm. You have your humerus and your ulna. Notice that humerus is in, sorry, not the humerus, this is the radius. The radius is orange. So the forearm on a human has an orange radius. A cat also has that same bone. A whale has that same bone. And a bat has that same bone as well. It's not a coincidence that we all have similar forelimb structures. It's because we have a common ancestor that had these bones. Humans have an upper arm here. So does a cat. So does a whale. So does a bat. We have carpals, which are our wrist bones here. Cats have wrist bones. Whales have wrist bones, and so do bats. And they have fingers or phalanges also. So these color-coded bones here, this represents homologous structures. They are similar because we got them from a common ancestor, right? Cats, whales, bats, and humans all have a common ancestor, but they have different functions. They don't look identical because they do different things. Bats fly, whales swim, cats, I don't know, jump around, and humans do jazz hands. So let's write this down in our notes. Again, here is that same picture you guys can see up close. So this is the opposite of homologous structures. You don't have to write this down in your notes, but I want to go through it. This is called an analogous structure. An analogous structure is a structure that has the same function, but different structure. So for example, a dragonfly uses its wings to fly, and a hawk uses its wings to fly, but they are totally different. A dragonfly has no bones. It has just basically some pieces of wing here that are very, very flimsy, very, very small. There's not much holding these on. Now the wing of a hawk is much different. It's a lot stronger. So analogous means no evolutionary relationship. So similar function, right? They both fly with their wings, but they don't have any structure that is similar. All right, next thing on our notes is called vestigial organ. So a vestigial organ is a structure that has little or no function, and these are remnants of structures that were functional in ancestral species. So some examples: snakes and whales, they have pelvic and leg bones of walking ancestors, but they don't walk today. Humans have a tailbone, right? That doesn't serve really a purpose today, but in our ancient ancestor it probably did, right, to have a tail. And our appendix as well is what we call a vestigial organ. It doesn't really do much for us. It might store a little bacteria, but it does not serve its original function, which was part of the digestive system. So let's write this down in our notes. Vestigial organs are structures that we still have, but have no, or they don't have the same function that they originally did because we've evolved away from our ancient ancestors. So we don't use that anymore. So notes. Here are some pictures. These are fish, cave fish. There's no eyes. There are eyes in cave fish, but they don't really need them. Here's those pelvic and leg bones in a whale. Again, they don't use them. They're vestigial, but they used to use them. And then here's a good one. Why do ostriches have wings, right? They don't use them. They can't fly, but their ancestors probably could, so they still carry those vestigial organs. Okay, next one is what we call comparative embryology. So what comparative embryology is, it's when we compare animals before they are born because they look similar, believe it or not. Similar embryological development in closely related species. So when we're in the embryo, before we're born, everything kind of looks the same, and they don't look the same because it's random. They look the same because we all have a common ancestor. So take a look here. The human, the bird, reptile, and fish. You'll see a couple things. You'll see these blue gill slits here. All of them have that. We also have some knobs for like appendages here, here, and here. So reptile, birds, and humans. And even fish, right? We have a common ancestor, and we do that because, or we know that because we have similar embryological development. So, similar development in the embryo represents closely related species. So let's write this in our notes. Okay, here's a little game I like to play. So you have 8 species here. I think we have a salamander, we have a fish, I think we have a tortoise, I think we have a frog maybe, and there's a rabbit, a cow, a dog, and a human. So here is early on in development, and see if you can tell which one is which. So pause and see if you can identify which one is which. Or at least try to find which one's the human. Okay, here's a little bit farther on. So this is a little bit farther in development. Again, you can see a few changes here. These two are very different from the rest. But if you look at these 4 here on the right, they look pretty similar. So again, can you tell which one the human is? Okay, and here's the last picture. So if you look at this, here's the human on the right. I think this was the dog. I think this was the cow, pig, chicken, turtle. This is the salamander, I believe, and this is the fish. So as you can see, they all look pretty weird in the embryo. They all look pretty similar, and that represents that we all have a common ancestor. That's why we all look so similar. Look at this first one here. We all have these same gill pouches, every single one of them, even the fish and the salamander. Okay. All right, next one is called DNA sequencing. So DNA sequencing is when we compare the DNA of organisms to see how similar or different their DNA is. The idea is that if you have DNA that is more similar in the A's, T's, C's, and G's, that represents more closely related species because we had a common ancestor. So animals that are more closely related have similar DNA. Let's write this in our notes. Okay, so here's, take a look. You have all these animals here. You have human, monkey, horse, pig, cow, sheep, dog, rabbit, yada, yada, yada. This represents DNA sequences. And if you look through each of these, and we're not going to do this, all the letters represent sequences of DNA. And if you look at them, there's a lot of things that match up. If you look at a human and a rhesus monkey, almost every letter matches up. But what's funny is that if you look at the blue letters here, the blue letters represent similar letters for everything. So look at this. This is wheat. Wheat is a plant. We share similar DNA with wheat, right? And that can only happen if we came from a similar ancestor. So believe it or not, all life, plants and animals, came from a common ancestor. And we know that because the DNA is the same. Okay, last one, artificial selection. So in artificial selection, it is where humans select the traits that we like in organisms, and then we breed those into organisms. So like cows, dogs, horses, you could even say plants, because this causes change over time, right? Think about dogs, right? They evolved from the wolf, but they don't look like a wolf anymore. Think about like a chihuahua, right? Its common ancestor is a wolf. How did that happen? It happened because humans have selected certain traits that we like in those organisms, and we breed dogs that have those traits to give us more of those traits. So let's write this in our notes. Here are some examples. Believe it or not, all of these vegetables here, cauliflower, broccoli, cabbage, kale, and kohlrabi, they all came from a wild mustard plant that we have selectively bred to give us these different varieties. These are all related. These are all related. They taste kind of similar too. Peppers, right? We know that peppers all came from a common ancestor. And here's the dogs. Again, all these dog breeds are all from a similar ancestor, and they all look different because we have artificially selected certain traits that we like. And what this shows, guys, this shows that we can make things evolve over time simply by artificially selecting the traits that we want. So if we can do it, we know that nature can do it as well, and that evolution does occur because dogs have changed. These have absolutely changed over time. Evolution is absolutely real because we know that dogs have changed over time. Okay, guys, this is the end of our notes. Make sure you guys tape this note sheet into page 163 and then move on to the next step in your instructions.